All right, so let's get started. I'm filming this RLA session in the back corner because a few people can't make it tonight due to the Gen Chem exam, but it's not going public, so don't worry about that. It's just going to Vidisha. True, Vidisha. I don't get to see Vidisha just completely freak out when I describe stuff this time, so I'm sad. Alright, so this week the lab will introduce you to the world of integer linear programming for basically solving logic puzzles. So essentially what integer linear programming is it's going to be optimization, but you'll have linear constraints and you'll have certain linear constraints and you'll have a certain linear objective that you're trying to maximize. So that's why it's called linear programming. So I'm gonna talk about what linear programming is for about the first 10 or 15 minutes, just to give you a good background so you can have some nice intuition going into the lab. Then a little bit on the actual lab itself. I really think that you can't talk about the lab itself until you talk about what linear programming is on a more fundamental level. So, did Dr. Pandich talk about what linear programming is? Or what do you currently understand it to be? What do you currently understand it to be? So, yeah, I said what it was. It's a linear minimization with linear constraints. And this is what linear programming is. So you might be like, I have, $10 to buy apples and bananas. And apples are $1, bananas are 50 cents, and apples produce 2 units of happiness, and bananas produce, let's say they both produce 2 units of happiness. Or say apples produce 3. That'll make it interesting. Okay, so let's say that we buy, also there are only 5 bananas in the store. So this is a linear program. We're trying to maximize happiness, and there are linear constraints. Basically, in this case, our one linear constraint is that there are only 5 bananas, and our second linear constraint is that we only have $10. So if we end up writing out what this is, so here we're trying to maximize, let's say we have X apples bought and Y bananas bought. We're going to maximize our happiness function, which is 3x plus 2y, right? Under constraint, and here our constraints are that we only have so much money, so the total cost of everything has to be less than or equal to $10. So x plus x plus 0.5y is less than or equal to 10. And then our second constraint is that there are only 5 bananas, i.e. y is less than or equal to 5. Also, we only can buy positive numbers of apples and bananas. So x is greater than or equal to 0, and y is greater than or equal to 0. And I think that's all of our constraints. Now there's one last pretty major assumption. If we could buy fractional apples and bananas, then this linear program would be a continuous linear program. It's easy to solve, and there are entire classes just devoted to solving continuous linear programs using stuff like the simplex method. But this right here is an integer linear program. So integer linear programs are where numbers, or where values of variables optimized are integers. All right, so this is an integer linear program, and this is the type of thing that we solve at the very end of this lab, more or less. And it turns out that the optimal solution to this integer linear program is 8 apples and 4 bananas. B-A-N-A-N. So you have some solution. Now, most linear programming solvers are going to have sort of this constraint on them that they require everything to be given to them in a very particular way. So, for example, the function has to be minimized. So 3x plus 2y, we're maximizing it here. If we want to minimize 3x plus 2y, we can maximize negative 3x plus 2y. So our constraints all have to be less than or equal to stuff. So we're going to have to use, x plus 0.5y is less than or equal to 10, y is less than or equal to 5, negative x is less than or equal to 0, and negative y is less than or equal to 0. And once we have all those formatting things done, we have an integer linear program, and MATLAB has this great function called intln_prog that will solve your integer linear programs for you. So that's all fun and good, but the lab is not about apples and bananas, it's about graphs. And the connection between integer linear programming and graph theory is often the hardest topic for students taking up this lab. So how does integer linear programming become graph theory?
Wait, question.
Yes.
So like when you minimize, you have to like flip out the sign?
Yeah, you have to flip both signs on each side of the equal sign, or inequality.
And you flip all the signs for the constraints?
Yeah, yeah. We'll get to that. As long as you pass MATLAB an input that is logically equivalent to this, then you're good. It's just a matter of passing stuff into solvers, which are built with very specific intentions in mind. Okay, so we have this integer linear program. Graph theory. What does this have to do with graph theory? So the way that this has to do with graph theory is that instead of having buying like 0 to 10 apples and 0 to 5 bananas, we're instead going to use a different set of constraints. And we're going to define these constraints a little bit differently. So that, yeah, we're gonna define these constraints a little differently. Instead, what we'll do in graph theory is often you're trying to pick a best set of like nodes or edges. And so instead of minimizing or optimizing x and y, we're going to optimize this giant vector of zeros and ones, where a 1 means that the edge or node is included in the set, and a 0 means it's not included in the set. And that's where a thing like this relates to graph theory. So let's work maybe on one topic. Maybe we can do minimum dominating set. Just work it on the board. So if I have these 5 nodes, let's say that we have node 1, node 2, node 3, node 4, node 5. And they're connected in this way. Okay. And we have some adjacency matrix for it, which for graphs, adjacency matrices just, you remember it from last week, whenever we built our prim thing, the minimum spanning tree. But basically, what we're going to do is we're going to look at turning this graph into constraints on a minimum dominating set. So, does anyone know what a minimum dominating set is? Jeremiah?
Isn't it the vertices where the least number of vertices you would need to reach every single point in the graph?
Yes. Yes. Or more explicitly, it's a set of vertices. There may be several of these sets that exist. It's minimal, not minimum. So it just means that it's a set of vertices such that this set is the smallest sized set that the total neighbors of all of these vertices, including the vertex itself, combine to form the entire graph. So it's the smallest set of vertices such that every node in the graph is at most one edge away from any of these vertices. So it's like, say you had a bunch of towns and you had some doctors. You wanted to use as few doctors as possible, but you didn't want anyone traveling more than one town over to reach a doctor, and you wanted to use the least doctors possible. You would use the minimum dominating set. So that would be the towns you put the doctors in. So if you have this graph, which nodes would be the minimum dominating set? Or name a set of nodes that is a minimum dominating set of this graph. Huh? 1 and 3. So yes, 1 and 3 is a minimum dominating set. Or minimal dominating set. Is there another set of nodes that you could use that would work? Yes. Yeah, there is. So you could actually do 3 and 4 also. And I think that with that, yeah, that's all of them. Because if you put this one or this one in it, then it would yeah. So yeah, 1 and 3 and 3 and 4 are 2 minimal dominating sets. So let's look at how we would end up computing this. Let's use a similar constraints type thing. Or actually, let's describe these both as vectors. So we're going to be getting a vector x out of our integer linear program. This vector x tells us whether or not each node is in the minimum dominating set. So for 1, 3, that would imply that x would be basically a 1 in the 1 spot, a 0 in the 2, a 1 in the 3, a 0 in the 4, and a 0 in the 5. Do you see why this would be? Like why this would be this way? So if our interlinear program returned 10100, then essentially what this means is this 1 says that node 1 is in the minimum dominating set. This 0 here at the second position says that 2 is not in the minimum dominating set. This 1 in the third position says that node 3 is in the minimum dominating set. This 0 at the fourth position says that node 0 or node 4 is not in the minimum dominating set. And this 0 in the fifth position says that node 5 is not in the minimum dominating set. Do you see what that means now? Like, is this making sense? Okay, so I'm going to refer to each of these values whenever I write my system of equations that will logically describe what has to be true for a minimum spanning tree to exist, or some minimum dominating set to exist. So I'm going to call this x of 1, x of 2, x of 3, x of 4, and x of 5. Alright, so essentially what we're going to do for a minimum dominating set is we're going to set up a system of equations that such that basically we're going to have one equation per node, and that equation will say that either that node or one of its neighboring nodes is in the minimum dominating set. And when we combine all of them, then that'll basically get us a constraint for what the minimum dominating set is. So we have 5 constraints here that have to be true for us to have a dominating set, which is just, it doesn't have to be the minimum. It could be 3 nodes and be a dominating set. So what we could say is, okay, so if we're talking about a minimum or a dominating set, and we're looking at this in respect to node 1, then either node 1 or one of its neighbors has to be in the set. So 1, 3, or 4 is in the set. Alright, then moving on to node 2, then we know that node 2 or node 3 would have to be in the set for it to be satisfied. Okay, and then at node 3, then we need node 1, node 2, or node 5 to be in the set. So 3, or 1, 2, 3, or 5. Okay, then for node 4, we know that node 1 or node 4 would have to be in the set. Alright, and then for node 5, we know that node 3 or node 5 would have to be in the set. Alright, so we have this. You see what this means, right? Like, each one of these is what each node requires for a neighbor to be in the minimum dominating set. Do you get that? Okay, good. I think you're getting it, Christina. Yeah, I was afraid. You looked really out of it. Alright, so we have this. Let's convert each one of these into a thing that has to be logically true about x of 1 through x of 5. So, in order for this to be logically true about x of 1 through x of 5, we can translate this basically saying that x of 1 plus x of 3 plus x of 4 is greater than or equal to 1. Do you see why that has to work? Like, why x of 1 plus x of 3 plus x of 4 is greater than or equal to 1? It's because, think about it, if you sum up x of 1, x of 3, and x of 4, you get the number of those nodes that are in the minimum dominating, or that are in the set that we're testing. Okay? right? If we sum up those values from the vector, we get the number of those nodes that are in the set that we're testing. So if we sum them up and say it has to be greater than or equal to 1, what that's saying is, in this constraint, what that says is that we have at least one of the nodes that are at or adjacent to node 1 in our set. At least one of those nodes has to be in a set for that set to be dominating. And so this is the big conceptual leap of why of converting graph theory to integer linear programming. This idea of converting this or statement into the sum being greater than or equal to 1. All right, so if we have that, we can continue with just writing out all the rest of these equations. And it's pretty easy. All right, so that's all your equations. Okay? And all of these have to be true for a set to be a dominating set. And yeah. So what are we going to do to check and make sure things are minimal? Okay, so to make sure things are minimal, we want the least number of nodes possible in our graph, right? So if we sum up our x vector, then that's the number of nodes we have in our graph. So we're going to minimize the sum of x, or 1, 1, 1, 1, 1 times x. And this is matrix multiplication. So we're going to minimize that with these constraints. And there's actually 5 more constraints we have, or 6 more we have to give MATLAB. And that is, or 10 more. X of 1 is less than or equal to 1. X of 1 is greater than or equal to 0. X of 2 is less than or equal to 1. X of 2 is greater than or equal to 0, so on and so forth. And this is the sum total of everything that we give to MATLAB to solve our linear program. And once we give this to MATLAB, we have our minimum dominating set, basically given back to us in the form of an x vector like this from our linear program. Surely enough, if you checked this x vector right here, it would actually it would satisfy all of these. It also would minimize this.
What is 1, 1, 1, 1?
So what this does, matrix multiplication is like the sum of the row elements times column stuff. Right? X is a column vector, so it's 1 times x of 1 plus 1 times x of 2 plus 1 times x of 3 plus 1 times x of 4 times 1 times x of 5.
Why do I have to do that?
Because we want to, when we sum that up, it's the sum of x of 1 through x of 5, right? When we do this matrix product. And so it's all you do. Like for this example, since we have 5 nodes, it's 5 ones. But if we had more nodes, it would be more ones.
Can I just do X transpose?
Yeah, you could do x transpose times a column vector of ones. Also, you could do x transpose times x, but that's weird. Because it would give you basically the sum of all the elements in x squared, which indeed is the sum of all the elements in x. Because they're all zeros and ones. But it's a little silly. Okay, so that's when you're programming. Again, we're gonna have to convert it into basically a matrix is what this will end up becoming. And I think you know how to convert this set of linear equations into a matrix. And actually, when it's all said and done, for a certain adjacency matrix, a minimum dominating set is just going to be minimize for n nodes and adjacency adjacency matrix. We're going to minimize, actually this is just all the nodes that are adjacent to and the node itself. So if you have a system of equations with all nodes that the node is adjacent to, that's just the row of the adjacency matrix it's from. And this right here is, you know, that. So you're basically going to minimize ones of 1 comma n times x with constraints so there's going to be a matrix-based constraint, which is just going to be a plus or adj plus I of n, which is going to be the adjacency matrix, which will say, you know, one of the nodes that's adjacent, and that'll program basically all of these that aren't the node itself that this constraint is for, plus I of n, which just says it could also be, you know, just trust me on this, that this gets you the right matrix for that system of equations. And you could work it out yourself if you really wanted to. With constraints adj plus I of n times x has to be, in this case, it has to be greater than or equal to 1. And I think MATLAB's NLinprog is actually less than or equal to, but I'm not sure. I'm not sure if this should be, if it was less than or equal to, or is greater than or equal to ones of n by 1, right? A column vector of ones to represent all the right sides of those linear equations. Let me just get, make sure. AX is less than or equal to B. So it actually has to be negative adj plus I of n over here is less than or equal to 1s. And then there also is, there's an AEQ and a BEQ that you're just going to ignore like you did in FMinCon last week. Then you have your lower bound and your upper bound, with lower bound being zeros of 1 by n, or n by 1, right? Just a column vector of zeros that says the corresponding value in x has to be greater than or equal to this, and an upper bound of 1s of n by 1. And that's basically the entire show for integer linear programming to solve the minimum dominating set problem. Okay, so we have that. Does everyone understand how I went from logic to linear equations? Do you think you'd be able to do this on your own for a different problem? In this case, the problem is the max clique. So what a max clique is basically, it's a set of nodes such that all of those nodes are connected to every other node. Okay? And basically what you would end up having to do when you run the max clique problem is No, I forget how to solve the max clique problem, but it'll come to me sometime. I think it's outlined more in the PDF, and I do have some archive videos from last year that I might send out on that. Okay, so we have that. Now how to implement in MATLAB and what you're going to be doing with it on this lab. Alright, so what you're actually doing on this assignment is you're loading a graph. I think it's saved as an edge list, and you're going to have to convert it into an adjacency matrix for this lab to work. Otherwise, you aren't. Like, it's not going to work. So an edge list just says that there's an edge between these 2 points, and so, or these 2 nodes. And it turns out that you could just take a matrix of zeros, plop it down, and then iterate through each edge in the edge list, which is actually basically m by 2, where you have m edges, and you have 2 numbers there, or it's actually m plus 1, because I think the first one's like the number of edges and the number of nodes or something. But basically, you just iterate through each row. You're just like, okay, I have a edge between these 2 nodes. Let me just go into my adjacency matrix, put a 1 in that position in the matrix, and say I now have an edge between these 2 nodes. It's very similar to how you built T last week. Also, you'd have to go and do those 2 nodes in the other order and put a 1 there too. So it's just like building T last week, except you iterate through some stuff. Okay, so there's minimum dominating set. Here's some other funny stuff. Oh, yay. Yeah, there's a graph. Yeah, so I think they talk about max clique here, too. Maybe, yeah, right here. And a clique is just a set of nodes that is all connected to each other. You should really read the PDF on this one. I mean, this is really a PDF for the reading. You know, sit down, block out 2 hours for it, because it's pretty heavy. But it will tell you what you need to know. All right, so correct derivation, correct output. All right. Then there is a way to color nodes. There's a particular, I think there's some like graph set node color. Highlight, yeah, you just use the highlight command. That'll actually take in a graph. So yeah, use highlight. I think there's also color too. Yeah, something like this. This particular syntax is what you'd use to recolor certain nodes in your graph. And yeah, that's the graph I like. All right, so explained linear programming, intlin-prog. Maybe I could implement intlin-prog for this graph. It's really just a one-liner, but you know, might as well write a little script. I'm gonna do size. Alright, and then okay, so I'm just gonna write the edge list. I'm just gonna do E is equal to, well, there's a particular format, but we have 1, 2, 3, 4 edges, and we have 5 nodes. So we're gonna do 5, 4 as our first row, and then this is how your graph comes packaged. The first edge, the first node is first edge is 1 to 2, or 1 to 4. Yeah, 1 to 4, 1 to 3, and then we also have an edge from 2 to 3 and 3 to 5. Okay, and then I can do something like edge is equal to basically zeros of E of 1, 1, which is just the number of nodes that we have. And then I can do something like 4, I is equal to 1 colon size, or 2 colon size of E in the first dimension. That'll basically iterate through all the rows starting at the second row. I'm just gonna do, I'm gonna call these two nodes J and K. So J is just E of I comma 1. K is just E of I comma 2. And then I can do the 2 edits in edge. Does anyone want to give me a line on this one? If I have the variables J and K already set to the 2 nodes I'm adding an edge.
Adds JK and KJ.
Yeah, so edge of JK is equal to what?
It's equal to 1.
1, yeah. And then I close that out. I have my adjacency matrix built. I'm then going to do, actually, I'm going to set E of 1, 1 to N. Or N is set to E of 1, 1. I was writing the solver the other night, and that was actually the error I made. Equals signs in the opposite direction. So now all I have to do is just int linprog. Okay, and then I have certain inputs. So first is my function input, and this is just your f is basically just the row vector that you multiply your column vector x by. So I'm fairly sure that that's all it is, right? F prime times x, so it has to be a column vector. So it's going to be 1s of n comma 1, and then my second thing that I'm doing is the integer constraint, which is going to be all nodes. So you can just do 1 colon n, and that'll say I want all nodes to have to be integers. That is important right there. Okay, then your a, which is going to be negative edge plus I of n. All right, and then your b is going to be basically if this has to be less than or equal, or I actually made it negative, so it has to be less than or equal to negative 1s of n1. So it's going to be negative 1s, it has to be n by 1. And then my last component of this is going to be AEQ and BEQ, which we can just put open close bracket to tell us, you know, we don't want that. And then LB is just going to be 1s of n by 1, or 0s of n by 1. And UB is just 1s of n by 1. All right, and there's in linprog. I'm going to set my output to x. And then I'm just going to display x at the end. And there we have it. So linprog came up with x being non-zero at 3 and 4, And indeed, 3 and 4 is a minimum dominating set. So that's how you use int winprog. And that's how you use it for a minimum dominating set. And that's basically your entire code. I probably should have never given that to you. But don't worry, Kplex and Clique are harder. Alright, so if we wanted to perhaps get the node value, or we can just do find abs of x minus 1 is less than 0.5, which it just sometimes is inexact for some reason. It's like 0.9999. This should just be a catch-all. We should say our minimum dominating set is equal to that. We can do something like plot graph of basically our adjacency matrix. And then we just do highlight wait, we don't have highlight on here? Oh no. Wait, is this R2017A? Oh no. No, what MATLAB do we have? Well, why don't we have highlight? Am I just be doing a Pantich and spelling this wrong? I think that one day she typed in preferences. Highlight. I really H node IDs. H is equal to plot. Yeah. I don't know why this is not working. Highlight graph of ADJ, node IDs being MDS, node color G maybe? That might work. And then we do plot that. Maybe that will work. No, I don't know why we don't have the highlight function on here. This is confusing me lots. But you will use it. I think this computer's just being really dumb. It's not always that you have all the packages like correctly loaded and stuff. So yeah, any questions about the lab, its scope, like integer programming? Yes?
Can I see the second half of the linear function?
Yeah, there's not much going on.
I meant, sorry, could you scroll to the right?
Oh, yeah. So, yeah. Also, if you don't understand this code, you're gonna write yourself into a hole once you start having to build on it. So, understand it first.
So like int-lin will always minimize the function.
Yes, int-winprog is designed specifically to minimize the function f.
Okay.
On the constraints, ax is less than or equal to b, and x is greater than or equal to lb, and x is less than or equal to ub. Clique, I think you might have to do like edges or something, but I can't remember. I think you have to do something with edges once. Like, I think there's a program for each edge. Alright, yeah, if that's it, then that's been the RLA session. You know, if you have questions, I'm gonna eat at West. Yeah, probably just alone. Okay. it's due next week?
Yeah.
Yeah, it's after.
Oh, okay. We did talk about this in the RLA session, or RLA meeting on Tuesdays. Yeah, we did talk about that, but I didn't know she actually did it. So you're gonna, yeah. I guess I'm gonna have to kick you off to another Sunday, cause I'm actually leaving town tomorrow.